All right. Hello, everyone. How are you all doing? It's a pleasure to be here. Most of you have heard about the phrase AI for AI. So what does that mean in the context of chiplets and multi-die? Well, the explosive growth of AI technologies and AI applications is driving the need for high-performance computing, these large, complex systems, which are multi-die, as you all know. But designing these multi-die to meet these aggressive time-to-result constraints and targets, performance targets, cost considerations, are getting increasingly difficult, and we need AI for engineering these multi-die systems. From a recent survey that Synopsys conducted, the trends are unmistakable. The percentage of design portfolios in our customer base that is increasingly using multi-die for their designs is growing year to year. And we expect that trend to accelerate over the next few years. Now, all of this is made possible, of course, with the advances in packaging. It's no exaggeration to state that we are in a golden era of advanced packaging, and that era is likely to continue over the last decade at least. The objectives of the research, the focus, investment of advanced packaging are multiple, but foremost is the goal to ensure that die-to-die connectivity in terms of bandwidth, I mean interconnect density, as well as performance in terms of latency, approaches that of interconnects inside a monolithic die. And if you were able to do that, just imagine you have a monolithic die, you splice it with a pizza slice, a pizza cutter, any which way you want, they can talk to each other with the same performance as a monolithic die. So that's the holy grail. The other focus of interest and attention and investment is in expanding the size of these packages. Now, silicon interposer is hitting limits with 3.3x. We have organic interposer that can go to 9.5x, and you heard of system on wafer. And now we're talking about panel-level packaging. We're talking about square panels, rectangular panels, and we expect, in fact, as early as end of this year, maybe early next year, to have a square panel of 310 by 310 millimeters, and perhaps it might be 4x more, actually, 620 by 620 mm based on demand. And that's exciting because now with panels, you can really have any size of a chip on a single panel. And moreover, the cost per die is expected to come down quite dramatically because now you can squeeze more dies onto your panel compared to a round wafer. If you look at the primary advanced package types that are prevalent today, embedded silicon bridges, ultra-high density fan-outs like InfoOS that TSMC dominates, 2.5D interposers, 3D stacked memory, of course, with the growth and interest in high bandwidth memory, and 3D SoCs, logic on logic stacking. We expect all of these categories of advanced packaging to grow over the next decade or so. And of course, there may be new package types. For example, for panels, there is talk about diamond as a substrate. Now, in terms of the worldwide semi-packaging market, in 2025, it was $47 billion. And that's expected to grow to over $155 billion in 8 short years. And that represents a very healthy CAGR of 16.5%. Now, let's put this in perspective. So in around 2010 or so, AlexNet revolutionized the computer vision industry with their deep convolutional network, neural network engine for image processing. It boasted 60 million parameters, and it used your traditional CPUs and early GPUs from NVIDIA for their compute needs. Fast forward 5 years, we have BERT from Google, which required 340 million plus parameters. That's an explosive growth of parameters. And it needed TPUs, tensor processing units, neural processing units, and other compute for its computing needs. You all, of course, are familiar with the revolution of large language models and ChatGPT and GPT. GPT-4 requires or has more than 200 billion parameters. In fact, GPT-5, the expectation is the number of parameters will exceed trillion parameters. Now, to process, to train, to infer using GPT-4, you need a cluster of next-generation GPUs. You need advanced multi-die AI accelerators, hybrid chips, and so on. And today we are at the age of agentic AI, where the demand for compute, for performance per watt, for high bandwidth memory, for interconnect advancements is even more than ever before. Now these are, by definition, these systems are multi-die, but there are several challenges. The complexity of multi-die designs are growing, and some of the challenges were mentioned in the previous talk as well. So if you think about the number of decision points an architect or a system engineer has to make, all the way from the petitioning and technology selection, all the way down to your final result, there are many of them. And predicting the outcome of these decisions is getting increasingly complex. Making changes to your decisions late stage is very expensive, both in terms of your time to results, you need longer loops, as well as in terms of dollar cost. So let's touch upon a few of these challenges in the short time I have, starting with system petitioning and physical design. Here, the decisions to be made are which technology nodes to use. There are cost and performance trade-offs, as you all well know. Bump density, bump planning, TSV planning associated with power delivery, and a number of such decision points. Now, these are multi-die systems, so you have to be concerned with die-to-die connectivity. Now, UCIe is the de facto standard, but there are many considerations there as well. Considerations related to the substrate type, to the choice of interposers and microbumps, to the availability of your beachfront, to design decisions related to your PHY interface. And invariably, these UCI interfaces stream data, so you have to make decisions about the streaming protocol. Should it be AXI or Qi or some other standard protocol, or perhaps a proprietary protocol? Packaging, of course, is at the heart of your multi-die system. And as you well imagine, and many of you live this frequently, there are many decisions to be made here. Again, cost, performance trade-off, power, thermal considerations, multiphysics considerations. And speaking of power delivery is one of the biggest challenges and is growing. The complexity of power delivery is growing as the systems grow, right? So for example, it's important to ensure that you have power integrity at all parts of your design for all your workflows, accounting for IR drop, noise, etc. But you don't want to over-design your system, because then if you have too many IVRs or integrated voltage regulators, that consumes expensive real estate, which can have negative consequences on other parts of your implementation. But if you under-design, making changes late, if you decide you need more IVRs in your substrate, or maybe you need to push some IVRs up into your interposer, making those changes late is very expensive. It takes you back to your entire design cycle. Now, the multi-die systems are, as the name suggests, they are systems. And as with any system, you need to worry about or be concerned with software, right? So software changes software debug and bring up might require hardware changes. And you want to be aware of these hardware changes early in your design cycle. And therefore, software, hardware, co-design, co-engineering is important. Now, AI data centers demand 99.999% reliability. And the racks have thousands of GPUs and CPUs and IOs and monitors and sensors spewing out tons of data. It's necessary to process, analyze the data, develop actionable insights for product lifecycle management, and to predict failures. In fact, some of the advanced data centers want to know before the event happens, before a certain location on your data center becomes very hot due to a certain workflow, where it is, so that they can direct your liquid cooling system to cool that local region. And that's needed for energy efficiency. But last but not the least is security. Now, multi-die systems invariably will include chiplets from multiple vendors with a complex supply chain, and therefore the need to authenticate these chiplets is extremely important. Furthermore, there's a need to securely pass encryption keys in a multi-tenant environment. So given all of these challenges, and these challenges are only growing as the complexity, size, scale of the multi-die designs are growing. Think about a panel level multi-die design. AI is indeed not just necessary, but essential to re-engineer multi-die designs. As our CEO Sassine likes to say, re-engineer engineering. Now, Synopsys pioneered the use of AI using reinforcement learning for design optimization. This was used to improve your performance, power, an area for physical implementation, and that technique was expanded to improve analog circuit for analog circuit optimization, test pattern count reduction, faster verification coverage. We then added a layer of data analytics for design optimization for improving the PPA for designs, as well as to improve the silicon lifecycle management and the fab efficiency, as well as to ensure higher yield faster in fabs as well, using data analytics. Then thanks to the revolution of LLMs, large language models, as well as small language models and GPT and generative AI, we delivered high-value assistive and creative capabilities to our customers. Assistive here refers to like knowledge assistant, bringing the knowledge of the product at the fingertips of your engineer, of a junior engineer able to perform at a very high level very early. And expanding that to help the engineer with their workflows as well as to execute their complex runs and workflows as well. Creative capabilities include assertion generation. Assertion generation is becoming more complex to do it right, to have good coverage for these complex designs, test bench generation, RTL creation, and so on. And now, of course, we are in the age of agentic AI, and I'll talk about that some more in a few slides. But first, let me put some color to what I mentioned in terms of our AI technologies. A typical design optimization, when you talk about multi-die designs, these large-scale designs, involve identifying certain input parameters, running it through, looking at your output metrics, deciding whether they meet your targets or not, analyze your metrics, and then you have to figure out what your next iteration should look like, how to change your input parameters for your next iteration. In other words, you are trying to iteratively refine your solution. Now, you don't know whether you're marching in the right direction, whether this process will converge, how much QR you're leaving on the table. This could take weeks, months. So with AI technology, we are able to indeed take the solution from the current state in your solution space and march it towards the optimum point in your solution space, or near optimum point, very quickly with a few iterations. So it's still iterative refinement, but it's much faster. And invariably, it finds a solution which is very hard to find by normal traditional methods. So an example of such an application is in silicon channel routing. So here again, you have a silicon channel router. It may be an embedded silicon channel, for example, in an organic substrate, die-to-die connectivity, a few hundred nets perhaps, or a few thousand nets for these large systems. And the goal here is to not only maintain the length, to reduce the length skew, but also to meet certain SI targets, signal integrity targets, like insertion loss, near end, far end, crosstalk, and so on. And the parameters and variables you have at in your control, in your disposal, is things like wire size, wire spacing, ground shielding, and essentially how to use the layers efficiently. So in other words, you have to decide on the routing pattern. Now, typically, our customers rely on a few architects. Maybe there's one architect in the whole company who knows how to do this based on their past experience. And this architect, now there are many combinations that you can imagine, will, using the experience, figure out which combinations have the highest chance of success. They do the routes, they perform SI. Now, SI could be like tools like HFSS and so on. So these are expensive. Each iteration can take, for large designs, days perhaps. And then they try to figure out what the best pattern is. Now, with our AI technology, we are able to reduce the search space dramatically by using a physics-informed, a physics-based AI model. essentially using frequency domain S parameters, which are much faster than timing domain, but they're less accurate, but it helps you to reduce your search space. And then with the reduced search space, we further use AI, now with a more accurate physics-informed AI model, now using time domain eye-opening models to find your optimum solution. And in fact, using this method, our customer reported not only achieving better results in terms of insertion loss, crosstalk, and so on, the metrics they care about, that they were not able to achieve these results using their traditional methods, spending weeks to months, but they also achieved these results with a 5x faster throughput. Another example is in verification. Now, the goal here again is to determine what tests you need to get to a certain coverage, verification coverage, right? So again, traditional methods include, for example, constrained random methods to generate, in this particular example from our customer, about 1,200 plus passes or tests to reach your coverage target. Now, using our AI technology, we were able to achieve higher coverage with 3x fewer test cases. So again, better QR, faster, thanks to AI. Now, when we talk about multi-die, we have to think about multi-physics, right? I mean, there are EMIR, thermal, ESD, electrothermal stress considerations, mechanical stress considerations, and so on. Now, in the ideal world, you would want to, when you make your decisions, you want your decisions to be informed with this analysis. In other words, when you make decisions, you want to run this analysis to figure out the impact of those decisions. Now, that's not practical, right? These solvers are very sophisticated. They consume a lot of compute, and they take a long time to run. So this slide shares or talks about 4 layers of AI technology, which together helps this problem significantly. On the left, we refer to that as a bottom-up method. And these are, again, physics-based AI models, which help to improve the core technologies and components of your analysis engines and the solvers and so on. An example application is, for example, adaptive meshing for thermal analysis. Now, you would want to have a fine-grained mesh for thermal analysis to ensure you get an accurate estimation of the thermal hotspots, your max temperature, and so on. But then that's expensive. If your mesh is very coarse, you might miss your hotspots, or your max T or max temperature might be way off, and that could mislead you in terms of your design. You find a problem late, and now you have to go back and change a lot of things in your design. So here again, AI. So in the ideal world, you want to have this magically figure out where you can use a coarse grid for speed. You don't need the accuracy because you don't expect thermal hotspots there, and fine-grained where you want that accuracy to compute your max T and your thermal hotspots. But you don't know that because you've not done the analysis, and that's where AI can help. A simple example. The next one here is top-down methods. This refers to what I talked about in the previous slides. You have iterative refinement, so AI can help converge faster to a better solution. This helps with design optimization, model calibration, life cycle exploration through virtual models, digital twins, and so on. Now, like I mentioned before, these are massive systems. So imagine a massive multi-die system, whether it's on a wafer or on a panel, and you want to perform EMAG analysis or thermal analysis. I mean, that's going to take forever and going to take a lot of compute. So invariably, you need to have reduced order models to solve this problem. You need these models to have high fidelity, to be correlated, and that's where AI can help. Furthermore, here we're talking about lots of parameters that influence your outcome. AI can help reduce your parameter set. It can do sensitivity analysis to find out which parameters influence your output metrics that you care about. And once you have a reduced parameter set, you can develop or generate an ML model or a meta model, which can then be used as a proxy for your analysis for some of your workflows. Furthermore, this meta model or ML model can then help you determine what your input parameters should be in order to meet a certain output target. You have a certain output target that you care about. What should be the input values or parameter settings to achieve that in your system? And that's an optimization problem, and that's how this can help as well. And of course, with generative AI, for example, with Ansys GPT, you can do interactive Q&A, you can do automatic code generation for scripting and commands, and guide the workflow optimization as well. Now, it's very rewarding to see when customers report to us the productivity boost that they're seeing with some of these technologies. For example, leading CPU providers have reported to us 35 to 40% productivity boost using assistive technologies. And a leading memory provider reported 2x, which was indeed very good to see. Now, using creative technologies such as assertion generation, test bench generation, and so on, the productivity improvement is from days to hours, right? And from hours to minutes. So that's indeed very rewarding to see, and it compels us to do more in this direction. So that brings us to agentic AI. Well, what is an AI agent? How is it different from what we've talked about with generative AI and so on? Well, an AI agent has a specific goal in mind. It's designed to achieve a certain goal. It also has the ability to adapt to changing data and stimulus. Unlike the passive generative AI model, an agentic AI can adapt. And the third key property is that it can reason and execute multi-step tasks, complex multi-step tasks. Examples of some of the tasks that an AI engineer could accomplish in our domain, in our world of multi-die design, includes, for example, an engineer could be focused on analyzing and fixing scripts, constraints, or setup issues. This can take weeks for engineers, and you need certain expertise to do this well. Another AI engineer can be focused on improving the RTL for power and performance, and is customized to that design customer's needs. Yet another engineer could be focused on petitioning the multi-die design and doing cost trade-off analysis and making decisions. That's the other thing, agents can make decisions. Another agent could analyze and fix signal integrity violations on channel routes, for example, die-to-die routes. And yet another could autonomously design my multi-die power network. I described earlier the complexity of designing a power network for multi-die designs. And these agents, you can think of these AI engineers as a team of engineers working together, because some of these problems are interrelated, right? Then you can't solve them in isolation. So the engineers need to work with each other, as well as you can think of these engineers having a hierarchy of AI engineers. So it's very similar to how human engineers are organized today in our companies. But this slide provides a conceptual view of our vision of how AI engineers can help with our EDA workflows. So for example, you can have an AI engineer that processes your inputs, the user intent, makes decisions based on that intent. Yet another AI engineer, based on those decisions, plans what the steps should be. Yet another orchestrates it, in terms of making sure you have the right collateral and the compute and so on, the order of things of execution. And then you have an army of engineers that can go off and execute these complex tasks, and they all have to work together. Their decisions will be refined over time. They can work in an iterative environment where they can do the runs and then go back and fix things and change it again. And in the end, essentially, autonomously, that's the vision, solve complex multi-step problems. So as in the automotive world, you're familiar with the many levels of self-driving autonomy. Similarly, we have a few levels, 5 levels of autonomy for AI-driven multi-die design workflows. L1 is referred to as assisting, where all the key tasks are still done directly by human engineers, but assisted by AI. For example, of course, AI, the human engineer specifies the outcomes, and then they make decisions, optimize flow steps, perform simple and complex actions, but with assistance with AI. With L2, where the agents can now perform simple actions autonomously. For example, let's say you have a DRC problem in your design, a DRC violation of a particular type. An agent can fix that particular DRC agent autonomously. In L3, taking it to the next level of automation, now fixing that DRC might mean that you have to also change something else around. Maybe there are TSVs in the way and you have to redesign your TSVs or move some geometry or layouts around to accommodate the fix of the DRC. So now you have to invoke other agents to solve this problem of fixing a single DRC of a particular type. So you have multiple agents working together now to perform a complex function of fixing this rather complex DRC violation. With L4 level, with planning, now with adaptive learning, you could have like hundreds of these DRC violations in a design. They could be interrelated in some way. And so now you need to orchestrate and figure out how to optimize your solution, your fixing solution for these DRCs. And furthermore, when you have thousands of DRCs of many types, you have all these engineers now going off and fixing the different types of DRCs, but they need to talk to each other because there may be interaction and interdependence between how you fix the different DRCs. And that takes it to the next level of autonomy, which we refer to as full autonomy. In all of these cases, these are indeed making your human engineer a lot significantly more, orders of magnitude more productive. Jensen puts it nicely when he states, there's no question we're going to have AI employees of all kinds. I might rent 1 million Synopsys engineers to come and help me out. And of course, here is referring to AI engineers. In fact, perhaps in the not too distant future, there will be an AI engineer standing in front of you giving this keynote. I'm not sure how he or she will look, but next year. Chuck.ai. But as I conclude this keynote, I want to speak to each one of you, whether you are who's attending the Chiplet Summit, whether you are a designer, an architect, an engineer, or you're driving business strategy or ecosystem partnerships. The industry is at a pivotal point. We have to work together to drive standards and interoperability in this AI-enabled multi-die chiplet workflows. It's inevitable that autonomous engineering is necessary. In fact, I won't use the word necessary. It's essential for solving these massive, large multi-die designs which have continued aggressive time to result pressure, low cost as well as performance pressures, security, reliability, and so on. Let's build a vibrant community where we work together, we learn from each other, from our successes and failures, from best practices, and indeed, we have a rare opportunity to work together to shape the future of chiplet and multi-design engineering, as well as agentic AI innovation, not only for our companies, but for our industry. Thank you very much.